Items 7 and 8 of the Spring 2014 second exam is, of course, actually example 12.1 of the semester. We have a coaxial shaft that is 20 inches long with an applied torque at the end of 120 inch kips. Number one key in this problem is recognizing that this is an indeterminate problem. Without that, basically all the work that we do is completely erroneous. Right? And so we got to recognize that, gee, we have two shafts that have a common displacement at the end. This is an indeterminate problem. When I go look at the equilibrium drawing here, that applied torque of 120 inch kip at the end, I get TA and TS, so that the equilibrium equation is TA plus TS is resisting that 120 kip inches. The compatibility expression is that this twist that we have here of this segment AB turns out to be exactly the same length of both of the two shafts, and so this coaxial shaft, the steel and the aluminum. So phi BA is equal to phi S is equal to phi A. Right? The torque angle of twist relationship is that phi equals TL over JG. And so because I have the compatibility equation, then I can then drop in TL over JG for the aluminum equals TL over JG for the steel. When we work that out, then we'll get that T of the aluminum times length of the aluminum, which is going to equal the length of the steel. Those cancel out. Right? So that'll be TA over then 30,000 pi is going to be equal to T steel over 5600 pi, or that our T of the aluminum is going to equal 75 over 14 times T of the steel. It is much larger. Even though it's a less stiff material, because of its polar moment of inertia being so much larger, we end up with that T aluminum will end up being much, much larger. Right? So we're going to substitute that in then to the equilibrium equation, and we'll get that T of the steel factored out 1 plus 75 over 14, which in itself is 5.357, and that's going to be equal to 120. And so that will tell us then that the torque of the steel is equal to 18.87 kip inches. Right? And so as we continue to play that all out, then when we calculate the maximum stress shear stress in the steel, then that's equal to T rho over J anywhere in the steel. So we're at the outer fiber of the steel, so we'll have 18.87 kip inches times then the outer radius of the steel, which is the inner radius of the whole thing. Right? Go to the outer part of the steel, that's at 1 inches, and then divide by J of the steel, which is pi over 2 inches to the fourth. Note the units, kip, inch squared over inch to the fourth. Then when we calculate on through, we will have 18.87 times 2 divided by pi, or 12.01 KSI for the answer for the max shear stress in the steel. And that was all that we were asked for. Providing more than that is, in the consulting world, giving away your services for free, and consulting firms do not survive when you do that. Right? So even though this was essentially example 12.1, it wasn't exactly. So be very careful about answering the exact question that has been asked, or in other words, the scope of work that's been defined. Right? And then that was numbers for number 7, and then for number 8 we're asked to calculate the angle of twist of the shaft. So that's, again, phi BA is equal now to either the steel or the aluminum. I see now that I changed my symbol from steel from S to ST. We can hang with it here. And so our torque is 18.87 kip inches times our length of 20 inches, and divide by JG or GJ of the steel, which is 5600 pi kip inch squared. Right? And that will then work out to be 19.87 times 20 divided by 5600 divided by pi, or 0.0214, etc., radians as our final answer. The plus indicates to us that we have, if we look down the end of the shaft in a right-hand coordinate system, the torque is this way, so looking down the end of the shaft, that would be counterclockwise. That's what that plus is telling us.